Here we are starting sixth part of our spectrophotometry block, applications of UV visible light for determination of molecule. This is what we name UV visible molecular. Several types of molecular species absorb UV and visible radiation. Molecular absorption by these species can be used for qualitative and quantitative analysis. UV visible absorption is also used to monitor titrations to study the composition of complex chemical compounds. Absorption of UV and visible radiation by molecules occurs in one or more electronic absorption bands, each of which is made up of many closed packed by discrete lines. Each line comes from transition of electron from the ground state to one of the many vibrational and rotational energy states associated with each excited electronic energy state. Because there are so many of these possible vibrational and rotational states, and because their energies differs only slightly, they're very close to each other, the number of lights contained in typical band is quite large, and their separation of one another is very small. That's why you do not see separate line. You see only one relatively wide band, which is true for most of molecular compounds. Most interesting, of course, is absorption by millions of known organic compounds. Absorption of radiation by organic molecules in wavelength region between 180 and 780 nanometers, that is UV and visible light, results from interaction between photons and electrons that either participate directly in bond formation, so bonding electrons, and therefore they are associated with more than one atom, or they are localized about such atoms as oxygen, sulfur, nitrogen, and halogens. Those electrons we know as lone pair electrons. The shared electrons in carbon-carbon or carbon-hydrogen single bonds are so firmly held that their excitation energies corresponding to wavelengths in vacuum UV region below 180 nanometers. Single bond spectra are not widely exploited for analytical purposes because of experimental difficulties of working in this region. These difficulties occur because quartz and atmospheric components, which means air, CO2, that requires vacuum spectrometers evacuated and lithium fluoride optics. That's why we never measured single bond bonds. That's why we never measured saturated compounds, for example, saturated hydrocarbons. Now, what we can measure? We can measure compounds that will absorb UV or visible light strongly. A chromophore is, strictly speaking, functional group in a molecule that gives rise of color. In common usage, however, it means a functional group that absorbs in UV visible region. The word comes from Greek chromo, meaning color, and phoros, meaning bearing or carrier of. They are unsaturated organic functional group that absorb in UV or visible area. So when species have unsaturated bonds, they generally exhibit useful absorption bands. Conjugation between two or more chromophores tend to cause shifts in absorption maxima to longer wavelengths, so from UV to visible, from blue to red, so-called redshift. It's often difficult to determine precisely an absorption maximum because they are vibrational and rotational bands, broadening and absorption bands in UV and visible region. So what we can do? Usual alkanes, one single bond is not very suitable because we are still in vacuum UV. But if you have conjugated alkene, double bond, single bond, double bond, we are already in UV area. Same is true for triple bond. Uh, the good radiation is in vacuum UV, but we still have visible something in area of UV radiation. Carbonyl group gives some absorbance, however it's relatively small. Same is true for carboxyl and amide group. And double bond N radiation has very little absorbance visible. What provides a good absorptive band is aromatic. Benzene has strong absorbance in UV radiation. Other aromatics have even better. So in general, if you want your compound to absorb light nicely, you want to have aromatic ring or similar heterocyclic ring. But conjugated alkenes can serve the same purpose. So these are spectra of some typical organic compounds. Acetone, carbonyl group, has very little absorbance, hardly suitable for any quantitative work. But as long as we are getting aromatic group, this is aspirin, you have relatively strong absorbance, and this compound is useful for determination. Caffeine, even better, because we have conjugated ring. Carotene, pigment of carrot, has molar absorptivity almost 100,000, very strong. In general, we want to have molar absorptivities well above 100. Absorption by lone pairs is relatively weak, still useful for determining heteroatomic compounds. So for example, iodine and sulfur and some nitrogen containing compounds can be determined in very high energy UV spectra, very close to 200 nanometers. What about inorganic ions? Transition metal ions exhibit very low absorptivity because DD transitions, so electrons jumping from D to D orbital, are not allowed by laws of physics. So molar absorptivities are between 10 and 100. On the other hand, so-called charge transfer complexes, so when electron jumps from central atom onto ligand atom, from chromium to oxygen, for example, in dichromate, they usually have high molar absorptivities. Chromate, several thousand. Same electron jumping from iron to SCN group, several thousands. Electron jumping from iron onto phenanthroline, several thousands. Starch iodine complex, we already were talking about, several thousands. As a summary, you need to have charge transfer compound to be useful in molar absorptivity. There are some restricted applications of 3D transition ions. Metals like calcium or sodium or aluminum have their ions with absolutely no absorption in visible or UV spectrum. You need to have their reaction with something colored, metal indicators, then you can use it for molar absorptivity measurements. Which solvents we can use for UV and visible measurements? Solvents must be transparent in the region of spectrum where solute absorbs. Now, your compound must be sufficiently soluble in these solvents to give well-defined spectrum. In addition, we must consider possible interaction solvent with absorbing species. Polar solvents, water, alcohol, ketones, tend to remove vibration of fine structure, and if you want to look at this structure, you want to avoid them. Spectra in non-polar solvents, cyclohexane, often more closely approach to multi-line gas phase spectra. Now, you always need to do all your measurements of your standards and your analyte in the same solvent exactly. So again, which solvents are suitable for UV area? Water, ethanol, hexane, cyclohexane are fair enough. For visible area, you can use chlorinated hydrocarbons, acetone, dioxane, couple of other. As you can see, they absorb light in UV area and cannot be used there. Remember that in UV you need to use quartz. Quartz optics only, not glass. So, making a summary, what can we measure? Ideal case. You have your compound B with molar absorptivity better above 1000, and all other components of your mixture you want to analyze absorb light somewhere away from the band of your compound. So you measure at maximum. You always measure at maximum, not because this is highest absorptivity, because it's flat, so experimental deviations would be the lowest at this point. There is no problem in this system. Unfortunately, these are limited. Very often you have component of your mixture not interfering, but your compound offers very low absorptivity. Example was acetone. Acetone carbonyl group has molar absorptivity of 10 only, so you cannot determine small concentrations. In other cases, yes, your compound absorbs light nicely, but other components of mixture you want to analyze absorb light in the same area. So measurement is difficult. You need to remove this absorption somehow, and there is no general approach. So what can be done? The solution that is possible is you have your compound B reacting with some reagent to make another compound C. So your compound is chemically derivatized, transformed prior to measurements of absorbance. Now you again have a nice peak separated from all other components, and you can measure this peak. But you remember that you are not measuring your starting compound, you're measuring product of reaction. Examples of such are copper. gives very poor absorptivity, but you can have reaction of copper with colorless sulfur-containing compound, making bright yellow complex compound of such a composition that have molar absorptivity more than 10,000. Say, mercury doesn't absorb light at all, but it can react with very complex organic compound being colored, and this compound makes associate with mercury ions with different color than starting compound, and molar absorptivities in vicinity of 100,000. You can determine very small quantities of mercury very easily. Carbonyl group of acetone, you remember, doesn't absorb light strongly. We can have a reaction of carbonyl group with NH2 group, resulting of making a color compound. This compound is also colored, but absorptivity of associate compound, shift base, is slightly different from here to there, and you can measure this compound and determine acetone with it or any other aldehyde or ketone. There are plenty of other such examples.